Hello everyone and welcome to Seminar 4 of your course. In this seminar, we will explore problems related to responsive systems from transfer functions using given input signals, as well as stability of the system and oscillatory behavior. Let us move directly to question 1. We are given a transfer function 4 over 2s plus 1 and an input function represented by u of t. This input is piecewise constant in certain intervals. At all time lesser than 0, it takes the value 2. Between time values of 0 and 2, it takes the value 4. And for any time values greater than 2, it takes the value 2 again. We are told to assume that the system is at steady state before time equals 0. And at the steady state, the value of the output is 1. We are asked to derive the expression for output, that is y of t, for the given input. And we are asked to obtain this output in terms of the actual physical variable rather than the deviation variable. In order to solve for the response of the system, that is y of t, we start with a given input signal u of t. The signal can be represented by the figure shown. In order to convert the signal to its deviation form, we subtract the steady state value of the signal from u of t. Therefore, the signal in deviation form is given by u prime of t, represented by the second figure. This input in deviation form is represented as a series of step inputs. As you can see, the first step is a positive step of magnitude 2, and the second step occurs after 2 time units and is a negative step with a magnitude of 2 again. Once we have the input signal under deviation form, we take the Laplace transform of the signal. The Laplace transform of the given signal u prime of t is given by 2 over s times 1 minus exponential of minus 2s. As a reminder, for a step input u of t equals m, the Laplace transform is given by u of s equals m over s. Similarly, for a step input with a time delay of t units, the Laplace transform is given by m over s times exponential of minus ds. Then the output y of s is given by g of s times u of s equals 4 over 2s plus 1 times 2 over s times 1 minus exponential of minus 2s. Right now, we have the expression for output in the s domain. In order to convert it to t domain, we need to take the inverse Laplace transform of y of s. We can simplify the RHS as shown to obtain it in terms of the fraction 1 over s times 2s plus 1. This fraction can further be simplified using partial fractions. 1 over s times 2s plus 1 is equivalent to a over s plus b over 2s plus 1. Upon solving for the values of a and b, we get a equals 1 and b equals minus 2. Therefore, we substitute the partial fractions expression back into the inverse Laplace transform of y prime to obtain the expression for y prime as follows. Note that the time delay term exponential of minus 2s is shown after inverse Laplace transform by a step function with a time delay of 2. However, this y is still in deviation form as shown by the prime. We need to convert it back to a physical variable, not a deviation variable. And we do that by adding its steady state value, the value 1. Therefore, we have obtained the output response for the given system under the given input signal. Let us now move on to question 2. We are given two systems to study. Both are liquid storage tanks of similar diameter. The outlet pipe of system 1's tank is fitted with a valve that provides linear resistance to flow through the equation outlet flow equals 8.33 times tank liquid level. The outlet of system 2's tank is fitted with a pump that extracts liquid at a constant flow rate. Both systems are initially at steady state with liquid level H bar equals 6 feet and inlet flow rate Qi bar equals 50 gallons per minute. At time t equals 0, the inlet flow rate was changed to 70 gallons per minute. For both systems, we are asked to find the transfer function models between the liquid level and inlet flow rate. We are also asked to find the transient or dynamic response of liquid level for both systems, as well as their new steady-state liquid levels. Furthermore, given the physical height of the tanks themselves as 8 feet tall, we are asked to figure out which tank overflows first and when. As you can see, the two systems are represented in these diagrams. The outlet of system 1 has a valve that provides linear resistance to outlet flow, and the outlet of system 2 is fitted with a pump that extracts liquid from the tank at a constant flow rate Q. The transfer functions for the systems can be calculated through first principles, namely material balance through the law of conservation of mass. For system 1, the outlet flow rate is given by the expression 8.33 times liquid level, and for system 2, the outlet flow rate is a constant value denoted by Q. For both systems, the cross-sectional area is calculated with a diameter of 4 feet. The transfer function for system 1 is given by h prime of s over qi prime of s equals 0.12 over 11.28 times s plus 1. The transfer function for system 2 is given by h prime of s over qi prime of s equals 0.011 over s. For the next part of the question, in order to find the transient response of the systems, we start from the steady state of the systems. Since the flow rate Qi changes from 50 to 70 gallons per minute, the deviation variable Qi prime equals 20 gallons per minute. Upon taking the Laplace transform of Qi, we get Qi prime of S equals 20 over S. Substituting the value of Qi prime of S into the transfer functions, h prime of S over Qi prime of S for each system, we end up with the following expressions for h of t. Note that we take the inverse Laplace transform of h prime and add the steady state value of h, that is equal to 6 feet, to get the expression for h of t for both systems. The new steady state liquid levels in the tank can be found by setting t tending to infinity, since there is only one step increase given for tank inlet flow from 50 gallons per minute to 70 gallons per minute. Setting t tending to infinity in the expression for liquid level, we get the new steady state level for system 1 equals 8.4 feet for the given step input. For system 2, setting t tending to infinity, we get the new steady state level equal to infinity. In the final part of question 2, we are told to assume the physical height of both tanks is 8 feet. We are asked to find the time at which the tanks overflow, that is the time at which the liquid level in the tanks just reaches 8 feet. Therefore, we set h of t equals 8 feet in the LHS of the response expressions for both tanks. System 1 reaches 8 feet at 20.1 minutes, while System 2 reaches 8 feet at 9.4 minutes. Therefore, tank 2 overflows first for the given input. Let us now move on to question 3. In this question, we are given 4 transfer functions and we are asked to determine the stability and oscillatory behavior of the step responses using zeros and poles analysis. Let us first have a quick recap of stability analysis. For the system represented by the transfer function g of s equals 1 over s squared plus as plus b, the roots of the denominator are also known as the poles of the transfer function, and the nature of these poles determine the stability as well as oscillatory behavior of the system. The signs of the poles, that is the positive or negative nature of the poles, as well as their real or complex nature, decide the stability and oscillatory behavior of the system. If the poles contain only positive real parts, the system is unstable with no oscillation. On the contrary, if the poles contain only negative real parts, the system is stable with no oscillation. The presence of an imaginary or complex part in the poles of the system leads to oscillation. That, coupled with positive real parts, leads to instability, and negative real parts leads to stable response of the system. Furthermore, if the poles have neither positive nor negative real parts, but only contain imaginary parts, the system is marginally stable with oscillation. Let us now get back to question 3 of the seminar. For the first transfer function under step response, given by y of s equals 2 over s squared plus 4s plus 3, we solve for the roots of the denominator of this expression to get the poles of the response -1 and -3. Both S1 and S2 are negative roots with no complex parts. Therefore, the system under step response is stable with no oscillation. For part 2 of question 3, we are given the transfer function under step response y of s equals 1 over s squared plus 4s plus 4. Solving for the roots of the denominator expression gives us the poles -2 and -2. Therefore, since both S1 and S2 are negative roots with no complex parts, the system under step response is stable with no oscillation. The third transfer function under step response given to us is represented by y of s equals 1 over s squared plus 4s plus 8. Solving for the roots of the denominator expression gives us the poles -2 plus 2i and -2 minus 2i. Here, both S1 and S2 contain negative real parts with non-zero complex parts. Therefore, the system under step response is stable with oscillatory behavior. The final transfer function under step response given to us is y of s equals 1 over s squared plus 4. Upon solving for the roots of the denominator expression, we get the poles of the system under step response to be -2i and 2i. As you can see, both S1 and S2 contain no real parts with non-zero complex parts only. Therefore, the system under step response is marginally stable with oscillatory behavior. Let us now move on to the final question of the seminar. In this question, we are given a process model d square y by dt square plus k times dy over dt plus 4 times y equals u. Here, y and u are the deviation forms of the output and input variables respectively. We are asked to find the transfer function for this process model, as well as to discuss the bounded input, bounded output stability and oscillatory behavior of this system's response when k varies between -10 and 10. For the given system, we start by taking the Laplace transform directly. We can do so because we are told that y and u are already in deviation form. Therefore, upon taking the Laplace transform on both sides, we end up with the transfer function y of s over u of s equals 1 over s squared plus ks plus 4. For this transfer function, the poles are the roots of the denominator expression s squared plus ks plus 4. These poles can further be computed by the expression minus k plus or minus square root of k squared minus 16 over 2. The values of the poles S1 and S2 can be computed by considering different values for k. Let us first start with the range of k between -10 and -4. For all those values, the poles S1 and S2 both have positive real parts and zero imaginary parts. Therefore, the response of the transfer function, or rather the system, is unstable with no oscillations. When we consider values of k between -4 and 0, the poles S1 and S2 have positive real parts along with non-zero imaginary parts. Therefore, the response of the system is unstable as well as oscillatory. When we consider k equals 0, both S1 and S2 have no real parts but have non-zero imaginary parts. Therefore, at k equals 0, the system is marginally stable with oscillations. When we consider values of k between 0 and 4, we get negative real parts for the poles along with non-zero imaginary parts. Therefore, the response is stable for a bounded input with oscillations. And finally, when the values of k are considered between 4 and 10, we have the poles with negative real parts and no imaginary parts. And therefore, the system for those values of k is bounded input, bounded output stable with no oscillations. This brings us to the end of this seminar. Thank you for your attention. And if you have any questions, please feel free to ask those questions in the Q&A sessions we have this week, or you can just drop me an email.